This is Mr. Pillar, lecture number 5 for ECET Modern Energy, ECET273 Modern Energy. We're going to talk about transformers, and again it's based on Chapter 5 of the Square 9 of DeWitt text and Unit 5 of the Fardo-Patrick text. We're going to explain the purpose of transformers, explain some nameplate information on the transformer, and define the turns ratio along the way here. So, the first question is, what is a transformer? Here is a cartoon representation of a transformer. The cube shape in there would be what we would call the core. I'm going to assume we're going to talk about an iron or ferrous core. It could be an air core, and then you wouldn't have that device there or a plastic device to wrap around. But in this case, we have an iron core. Primary power comes in there on the left. Vp causes the primary current, the I sub P, to flow into the coil on the primary. That coil induces a flux. That flux is the IP, the phi there, and it creates a voltage essentially there. That voltage and phi rise and fall because we use transformers with an AC current. That rising and collapsing magnetic field causes a magnetic field to flow. That's the phi sub m that goes around into the iron core. That rises and falls, cuts the lines, the current carrying conductors of the secondary, and creates a voltage drop, a voltage potential from both leads off the secondary. That's shown there in E sub S for secondary. If we close that switch, it will become a V sub S with an I sub S. If the switch is open, you have a voltage potential. It doesn't mean you have current, but as soon as you introduce a load and close the switch, current happens and voltage drop happens. So primary is tied to the power system. Secondary would be tied to what we refer to the customer or load side. That's a transformer in very basic cartoonish terms. Here are two photos of transformers. There on the left, you can see a cutaway with the high voltage and low voltage windings. High voltage windings are the smaller gauge wires. Low voltage windings are larger gauge wires. Remember, P equals I times E. So as the voltage goes down, the current will go up, hence the need for higher gauge conductors for the secondary. Here I show 4 different ways a transformer, single-phase transformer, could be wired up. If you look here, you have on the primary side of each of these 4, I'm going to talk about in the top left corner, up here, you have an H1, an H2, an H3, and an H4. H designates high, so the primary goes there. We have a X1, X2, X3, and X4. So if we have 480 going in and we put these two coils, the H1, H2 coil, in series with the H3, H4 coil, we end up with the X1, X2, X3, X4 coil in series also. And we have a 480 to 240 transformer, which is essentially 200 turns. We're going to talk about what the turns have to do, but as you can see, it's the ratio, 1/2, causes the drop here. If we put the primary in parallel and the secondary in series, you end up with 100 turns to 100 turns, and that's a 1-for-1 ratio. We could take the primary in series and the secondary in parallel, and you have a 200 to 50 turn. We end up with a quarter drop down to 120 volts. Primary and secondary both in parallel, and you end up with a 50 to 100 drop, and you end up with 240 out. So the point being here is we have different configurations because this particular transformer and the transformer we're going to see in lab has 2 coils on the primary, 2 coils on the secondary. I want to make note that we could put them in series and in parallel, and we have the multiple ways of on the primary and the secondary of doing that. Also note the H1, H2, H3, H4, X1, X2, X3, X4. We're going to see what that matters, and that's actually polarized to maintain phase with the secondary and primary. Here's just another look of how it would be the single-phase transformers would be connected. Let's say these are power lines, A, B, and C power lines going down. Number A up here is a single-phase 2-wire system. You have just coming off C phase to ground, we have 2400 volts. We have a step-down transformer, hot to neutral, giving us 120 volts to our system. Here's a single-phase 3-wire system. They chose to use phase A and phase B to give us 4160. That comes down to a 240/120, just like a residential panel, or for this example, that large of a voltage would be more like a apartment complex type of a system to distribute to the panels in the apartments. Single-phase 3-wire system here. This would be much like what we would have on the pole at our home. Transfer down to us. Another, again, a 240/120 system. Notice the neutral is a center tap. The neutral is a grounded center tap of the transformer. So rated current for a transformer is calculated from the rated power and rated voltage. The rated power and the rated voltage are on what we refer to the nameplate of the transformer. There's a plate on every transformer that gives you those values. It's very simple. On single phase, you take the S rated and divide it by the V rated, and you get the I rated. So P equals I times E. We assume a purely resistive load when we make that assumption. 3-phase, same formula, except it's a 3-phase line current formula. So we add in the radical 3 to the V so that we can get our it's a 3-phase S rated and a line-to-line voltage on our nameplate. So here I referred to the turns ratio. Turns ratio is the voltage of the primary divided by the voltage of the secondary. That is equal to the ratio of the number of turns on the primary to the secondary. And by number of turns, I literally mean how many times the wire goes around to make the coil. We use a letter A for our turns ratio in notation, and it can be found also with the current. You can see, because E equals I times R, it goes across the board. We can find that turns ratio in numerous ways. Generally speaking, you take the primary voltage and divide it by the secondary voltage to get your turns ratio. I want to make note on the polarized notation here. See the dot? The H1 has a dot, the X1 has a dot. That means to get proper phasing, H1 and H2, so H1 must be your high leg, H2 would be your low leg or neutral, or it would be A to B, and then B, C, and then C, A if you were going with that in a 3-phase configuration, so that you end up with an in-phase nature coming out in your secondary. So let's take a look. What I'm kind of talking about here is we want primary and secondary voltages to be in phase. So primary and secondary in phase. Phase shift is due to polarity coils. If we flip them, if we change our phasing, being that we wired it up wrong, it was marked inappropriately, you'll see your phasor diagram ends up with S and P 180 degrees out of phase with each other. Now, why do we care? Well, in single phase, we don't really care, but the issue is that when we get into a 3-phase configuration with Ys, for example, you end up 180 degrees out of phase, and then if you were going to put those in parallel with each other, combining the 180, the 120, and 30-degree phase shifts on a number of possible connections, you're going to have, for example, let's think of two transformer banks operating in parallel. Well, if you have transformer bank A out of phase with transformer bank B, when you put them in parallel with each other, you actually have a voltage potential between X1A and X1B, and you'll end up causing a voltage potential will cause a current flow, and you'll short it out, and it's basically a phase-to-phase fault. High line, so we want positive sequent voltages is what we're going here with a North American standard of delta Y and Y to delta. Delta Y and Y delta are standard forms of transformers in three-phase. We'll get into that later in the future slides, but I kind of want you to go through and take a look and understand the phasing makes sense. You're going to see that in lab. So thank you very much for paying attention.